Welcome back to my series of presentations on problems in physics. In this video, I will talk about problems on elasticity. This is for the second semester, Unit 1. I will mainly be discussing problems on Hooke's law, elastic moduli and their relationships, work done or energy stored in a stretched wire, problems on bending moments, cantilever and torsional oscillation. Our first set of problems will be on Hooke's law. The statement of the law, as shown in the slide, is that within the elastic limit, stress is directly proportional to the strain. In other words, the ratio of stress to strain, which is called the Young's modulus of the material, will be a constant for a given material. Stress is essentially the force that acts per unit area, while strain is a dimensionless quantity, which is the change in length to the original length. The formula for Young's modulus in terms of stress and strain is shown in the We will once again be following the URAS method of solving a problem. So here's the first problem on elasticity. The problem is straightforward. It states that a 2-meter long steel wire hung from the ceiling has a 3 kg mass attached from the other end. If the radius of the wire is 0.2 millimeter and Young's modulus of steel is 20 into 10 power 10 Newton per meter squared, find the percentage change in the wire's length. There are 2 points here. The first point is to recall the formula for Young's modulus, which is Q is equal to mgl divided by pi r squared delta L. Now, when we substitute the values of all the quantities, we obtain delta L as 2.33 into 10 to the power of minus 3 meter. Having obtained delta L, we calculate the fractional change in length, which is delta L by L, and when you multiply fractional change delta L by 100, you get percentage change. So as shown in the slide, the percentage change is 0.12%. The second problem is quite straightforward. The problem states that what is the force required to stretch a steel wire 1 centimeter squared in cross section to double its length? The Young's modulus is given as 2 into 10 to the power of 11. Clearly, the change in length is equal to the length itself. So since delta L is equal to L, the formula for Q will give us F by A, or F is equal to Q times A. Now, when you solve for F, which is 2 into 10 to the power of 11, which is the Young's modulus, multiplied by the area, which is 1 into 10 to the power of minus 4, then we obtain the answer 2 into 10 to the power of 7 Newton. The third problem on elasticity states that calculate the longest length of steel wire that can hang vertically without breaking. Breaking stress for steel is 8 into 10 to the power of 8 Newton per meter squared, and density of steel is also given as 8000 kg per meter cube. Now, breaking stress means the maximum stress that the wire can take before it snaps. We need to find the longest length of the wire that will break under its own weight. So since stress is equal to force by area, we can write the force as mass into acceleration due to gravity, but the mass of any material is nothing but volume times density times g. So volume of the wire is area of cross section into length. Hence, when you substitute for stress as rho A L G by A gets cancelled and you get rho GL. So substituting from that for L, which is stress by rho into G, we solve for L as 1.024 into 10 to the power of 4. In this slide, we first define the rigidity modulus, which is nothing but the ratio of the tangential stress to tangential strain. It is denoted by the symbol N and has the same unit as Young's modulus, namely Newton per meter squared. The bulk modulus, which is the ratio of the volume stress to volume strain, is given the symbol K and also has the same unit, which is Newton per meter squared. The formulas for these are shown in the slide. The Poisson ratio is the ratio of the lateral strain to longitudinal strain. Now, what happens is when you have a wire which is fixed at one end and loaded at the other end, that is stretched longitudinally by a force, its length will increase while its area of cross section will decrease. In other words, it will contract this will decrease the radius r. We define the Poisson's ratio as the lateral strain, which is the ratio of the change in the radius to the original radius, to the longitudinal strain, which is the ratio of the change in length to the original length. We also have shown the differential form of Poisson's ratio, which is dr by dl times L by r. Note that Poisson's ratio has no unit. It's a dimensionless. Before discussing the next problem, let me explain to you the concept of the shearing modulus. Suppose I have an object like a cube or a cuboid shown in the figure, and suppose a tangential force F is applied on the top surface such that the bottom surface remains fixed. Now, if the top surface gets displaced, the object undergoes a deformation, and you notice that there is an angle between the deformed object and the original shape of the object called theta or phi. The shearing stress is defined as the tangential force F divided by the area over which it acts, while the shearing strain is nothing but the angle theta itself. Of course, we can even write it as L divided by L. So, as shown in the slide, the shearing stress is calculated to be 10 to the power of 4 Newton per meter squared, while the shearing strain is 10 to the power of minus 3. The ratio of the shearing stress to shearing strain, known as shear modulus, is given as 10 to the power of 7 Newton per meter squared. This is an interesting problem on bulk modulus. We are asked to find the density of lead under a pressure of 2 into 10 to the power of 8 Newton per meter squared, given that the density of lead is 1.14 into 10 to the power of 4 kg per meter cubed initially. The bulk modulus of the material is given as 8 into 10 to the power of 9 Newton per meter squared. Now, at the outset, we take the formula for the bulk modulus. Note that we take the modulus of K, which is dP divided by dV by V. From this, we can work out the change in volume, which is 0.025 V, V being the initial volume. So, the new volume of the lead would be Vf, which is equal to V minus the change, which is 0.025 V, or the new volume is 0.975 V. Now, if you know the density and know the volume, the mass can be calculated as simply the product of density into volume. So, the mass of the lead, rather the final mass of the lead, is density rho f, that is final density, multiplied by the final volume. Now, in any case of deformation, only the shape will change while the mass of the object remains constant. Since mass remains constant, the initial mass of the object would be initial density times initial volume. So, when you equate the mass that is obtained from the final density and volume and the initial density and volume, we can solve for the new new density as rho I into V, that is initial density into volume, divided by the present volume or new volume, which is 0.975 V, and hence obtain the density of lead as 1.16 into 10 to the power of 4 kg per meter cubed. Note that since the volume has decreased, the density has increased. In this slide, we have shown the relationships between the three elastic moduli, namely bulk modulus, rigidity modulus, and Young's modulus. We have also shown a formula for the Poisson's ratio in terms of K, N, and Q. Note that this set of formulas are very important for the exam, and you are likely to get a problem on this. This is a straightforward problem of calculating sigma from the three elastic moduli. We simply apply the formula sigma is equal to 3k minus 2n divided by 2n plus 6k. Notice that when you substitute the values of k and n, we obtain sigma to be 0.319. Notice further that there is no need for using the Young's modulus data, which is superfluous. In this slide, we have written down the formulae for work done in stretching a wire, bending moments, expression for Q of a cantilever of cross section which is rectangular as well as circular, as well as expressions for the couple or moment of the couple when a wire is twisted, and the period of oscillation for torsional oscillation. Like the previous set of formulae, this set of formulae are also very important for problems in examination. In this problem, we find the energy that is stored in a wire that is stretched. We are given the length of the wire as 5 meter and its diameter is 10 to the power of minus 3 meter, while it is stretched by 3 millimeter. We are given also that the Young's modulus of the material is 2 into 10 power 11 Newton per meter squared. Now, the formula for work done is nothing but half into stretching force into elongation. The stretching force F is obtained from the expression for Young's modulus, namely Q is equal to F into L divided by A divided A into L. Substitute rearranging, we get F is equal to QA into small l by capital L, or Q into pi r squared into small l by capital L. So when you come back to the formula for W, we can substitute for the stretching force and also for elongation, which is L. So the final formula for W is half times QAL squared divided by L. Substituting all the values, we get W is equal to 0.1413 joules. This problem is quite straightforward. A steel wire of radius 1 millimeter is bent into an arc of a circle of radius 50 centimeter. Calculate A, the bending moment, B, the maximum stress. We are given the Young's modulus as 20 into 10 to the power of 10 Newton per meter squared. Now we know that the bending moment is given by the general formula Q into I by R. In our case, since the wire has a circular cross section, I will be pi into small r squared divided by 4. So we get the bending moment as Q into pi small r to the power 4 divided by 4 times capital R. Substituting the values, we obtain the bending moment as 0.314 Newton meter. Now we know that the maximum stress is given by Q times small r by capital R, and so therefore substituting the values of Q, small r and capital R, we obtain the maximum stress on the wire to be 4 into 10 to the power of 8 Newton per meter square. This problem states that a steel wire of diameter 3.8 into 10 power minus 4 meter and length 4.2 meter is extended by 1.82 into 10 to the power of minus 3 meter under a load of 1 kg. And also it twists by 1.2 radian when subject to a torsional torque of 4 into 10 to the power of minus 5 Newton meter at the free end. We are asked to find the values of Young's modulus, rigidity modulus and sigma, that is Poisson's ratio. Problem is straightforward. We start with calculating the area of cross section, which is pi into small r squared, which when you substitute the values of pi and small r, we obtain as 1.13 into 10 power minus 7 meter squared. Now we know that the value of Young's modulus is nothing but F into capital L by A into E, where E is the extension. So all the values are given in this formula. So when you substitute for F, capital L, A and small e, of course note that F is nothing but M into G, which is the weight of the load attached, which is 9.8 Newton. We obtain the Young's modulus as 1.995 into 10 to the power of 11 Newton per meter squared. Then as far as the couple per unit twist is concerned, we can easily calculate it by the formula pi into n into radius of the wire to the power 4 into twisting angle theta divided by 2L. From this we can rearrange the equation to get n, which is 2CL by pi r to the power 4 theta. Substituting all the values, we obtain n as rigidity modulus as 6.842 into 10 to the power of 10 Newton per meter squared. Finally, we know that sigma can be written as Q divided by 2n minus 1. So substituting the values of Q and n, we obtain the value of sigma to be 0.457. In this problem, we calculate the work done in twisting a wire. One end of a steel wire of length 0.25 meter and radius 2 into 10 power minus 3 meter is fixed. If the rigidity modulus of steel is 8 into 10 power 10 Newton per meter squared, find the work done in twisting the free end of the wire through 45 degree. The point to note is the work done in this case is given by W is equal to half into C into theta squared, where C is the couple per unit twist, while theta is the angle through which the wire is twisted, to be substituted in radian. So we first calculate C by the formula pi n r to the power 4 by 2L, which gives us 8.038 Newton meter. Then we convert theta, which is 45 degree, into radian, which is pi by 4 radian. So theta squared is 0.62 radian squared. Now we substitute in the formula for W as half into C into theta squared to obtain the answer 2.49 joule. The last problem in this video is about calculating the moment of inertia of a system from torsional oscillation. A bar is suspended symmetrically from the lower end of a wire which is 1 meter long and 1.22 into 10 power minus 3 meter in diameter. The bar oscillates about the wire axis with a period of 1.25 seconds. If the rigidity modulus is 8 into 10 power 10 Newton per meter squared, we are asked to calculate the moment of inertia of the body. We begin with the expression for the period of oscillation in the case of a torsional oscillation. T is equal to root of I by C into 2 pi. Now from this we can get T squared is equal to 4 pi squared I divided by C. Or from there we can work out I as T squared C by 4 pi squared. So essentially we need to know C, and C is nothing but pi n r to the power of 4 divided by 2L. So substituting all this, we obtain the value of I as T squared into pi n r to the power 4 divided by 4 pi squared 2L, which on simplification gives T squared n r to the power 4 divided by 8 pi L. Substituting the numerical values, we obtain the moment of inertia as 6.889 into 10 power minus 4 kg meter squared. With this, we come to the end of this video on problems on elasticity. All the problems in this particular video were sourced from the textbook College Physics for second year BSc, written by Dr. N. Sundararajan, Dr. George Thomas and Professor Syed Aziz, published by United Publisher. I would like to acknowledge the author for their work. In the next video, I would be discussing problems on thermodynamics.